Hello and welcome to my 15th and final operating system development lecture. Today I will not be providing as much knowledge as in the previous videos, and this will not be that interesting. But I did want to sort of wrap things up and maybe think a bit about, well, the future. Now, in my first video, I sort of highlighted what I want to achieve, and I set very specific requirements for a very specific reason. I didn't want the series to die. I am a person who, well, can get quite demotivated from doing certain things if they take such, long amounts of time. Well, this took over a year. Well, I guess anyone could get demotivated, especially when there's, a lot of things going on in life that make it so that you don't have that much free time to do the research and record the videos and so on. So, I mean, I've been receiving absolutely amazing support, all the comments, all the thoughts on my videos, and the fact that I was actually helping some people obtain some knowledge on operating systems, that sort of kept me going. And I set very specific requirements at the start so that I know that I am going to try to actually achieve this, and I'm going to try to set requirements for an operating system that are like relatively decent and actually cover all of them at least a bit, so that I could at least be auxiliary material. Because, well, I did not expect anyone to make an operating system using only one resource. So, for some things that are a bit more complicated, maybe you'd like to see, a human being, sort of writing some things on the board and trying to explain some concepts more intuitively. I decided that'd be something useful, and that's why I decided to record a series. But yeah, so in the first video, I said that an operating system is some piece of software running directly on the hardware which allows the user to run processes, and it manages their resources. And then I listed out the resources, and I covered all of them. It was like data, CPU time, and I/O devices and memory, right? And there's actually one part of this definition that I have still sort of not covered in the series, and that is the part, and I highlighted at the very beginning that this will probably be the last thing that I'll be talking about, because we already, have processes, and we manage the resources. The problem is that the user cannot run them, right? Because I have not talked about anything related to a user interface. Now, most realistically, people will try to, have some basic user interface going way before all the other things I've talked about, such as process management and managing all those resources. Is it a good approach to introduce, user interfaces early? It's debatable. Because, well, in my opinion, user interfaces are not that important of a thing in an operating system. Obviously they are important, but I think when you're developing your own, the sort of core, of the operating system, which is like how it's actually going to run everything, how it's going to manage everything, that tends to be way more valuable in like the theoretical study of operating systems than a nice user interface, and that's something that can be left for later. I mean, obviously everyone has their own priorities, and it's fine to develop your operating system however you want to. But I think that once you have some basic user space, and you could run processes that are somehow valuable, and that are managed properly, that's like a very good spot to start actually thinking properly about your user interface. I mean, there are multiple sort of ways you could go about this, because well, what you sort of need is a shell, this thing that's going to make you be able to interact with the operating system. And well, this common solution is to have a terminal shell, right? So you're going to have some symbol, the command prompt, right? You're going to have something DOS-like, and you're going to enter commands. So you're going to have to do some basic like lexing and parsing within that software. And what you would do is you would have to implement just a couple basic instructions that allow you to interact with the file system. You know, just like on the disk operating systems and such, right? Or well, any modern operating system, but it doesn't have a user interface, right? So you're able to browse through the files, and you're able to go into different directories, and then you can, for example, run executables, right? Or you can run executables and pass as arguments some different files, right? So that's a terminal shell that you can implement. The other way to go about this is obviously to a way more like modern option, something that a lot of operating system developers think about nowadays, which is a graphical user interface. So in a graphical user interface, you're going to introduce some notion of a window. You could either just make a window manager, which is, you know, windows are going to pop up, we're going to auto-line, you're going to be able to control them. Or you could go about making a whole desktop environment, right? So you have some sort of taskbar, and you know you have some sort of desktop, and you can run different apps, for example, from the desktop, and windows will pop up and take a part of the screen initially, and you can, for example, maximize them, minimize them to the taskbar and such. So those are all things that are developed in a way that's just like pure programming. There's usually not much, you know, operating system development itself involved, in the sense that, you know, when you're going to be making a terminal shell, you know, the shell it's just going to be a program, right? It's like it already interacts through this layer of abstraction that the operating system offered. You're just making another program for the operating system. It's not like a core part of the operating system itself, theoretically. It's not like built into the kernel or anything. So since you're making a program on top of a kernel, you know, it usually just has to deal with standard things you do as a programmer. So you're making, you know, a basic interpreter of some shell language, and it's going to access operating system resources for system calls. So just like any other program would do so. And when it comes to GUIs, it's generally the same. It's as if you tried to just make a program that resembles all the windows and everything. It gets a bit more complicated when you think about the fact that every process, right, could draw on those windows. So you need to introduce some sort of operating system abstraction such that each process can get some video buffer that it can draw on, so that the process can draw just on the entire screen in an unprotected manner, but instead it gets its own virtual address range, which is sort of its, for example, video buffer. Well, that's one of the possible solutions, right? But you could give it some virtual address range for that process, which is the video buffer, and then the operating system would take that video buffer and draw it within the window that was allocated for the process. And well, you can then think of if you're thinking about graphics and things, you should think about supporting like standard libraries and sort of servers related to graphics. So things like the X server or porting OpenGL. So those could be relatively important things. And this sort of brings me to my next point, which is, well, what does a user actually expect from an operating system? Now we've been making, I sort of haven't highlighted this, but we have been making a very specific sort of an operating system, but well, it's the most popular one among the public. We've been sort of making a user-focused, like average user-focused, real-time operating system, soft real-time operating system. So like, what does a user usually expect when they open their home computer, right? Well, they want to be able to use software, right? They want to use software that we do in order to do the basic things, such as checking their mail or checking the internet or writing a document, right? So either you would have to write, a whole set of software for your own operating system yourself. It's one solution. But usually people are already used to some sort of software, and also you probably don't have all the time in the world to write your own software for your own operating system. So the way more reasonable approach is to consider porting software, right? So you port software from already existing operating systems onto your own. And the way you sort of do that is you want to tinker with the program itself as little as possible. You don't want to tinker with the program itself. Instead, you want to make and design the kernel in the operating system in such a way that porting programs onto your operating system is easy. So, for example, following things such as POSIX, right, the portable operating system interface for Unix, right, and supporting all the system calls and everything from the SUS, the single Unix specification. We remember that the programs are going to communicate with the operating system. We're going to communicate with the kernel through system calls. So obviously, the most important thing is to support some normalized system calls. The best one would probably be Unix system calls, as I've mentioned. You have a lot of software written for Unix-like operating systems, and you can very easily port that if you just support that sort of ABI, which is an application binary interface. So you might have heard of an API. That's sort of the way that the programmer gets to interface with something, and then the ABI, the application binary interface, is how the actual binary gets to interact with the operating system, right? So you have to sort of support that. You have to think about getting all the system calls that you want to match in order to port that sort of software, right? So once you have some software up and running, I mean, that's the point at which your operating system becomes sort of usable, right? So once you can write a basic document in it, right? Once you can open a web browser, that's where it sort of starts becoming impressive, because you've built the foundation, and this foundation is able to run all those programs that can be relatively easily ported because of how you've designed your operating system. Because I've already talked about this, developing this kernel and how it manages all those resources and how it runs user-space processes, how it schedules them, and now once you have all of that, you need actual processes to run, right? And obviously, a lot of those programs are going to require some sort of drivers or services that I haven't mentioned. So, for example, let's say there is some software that requires a drawing tablet, right? I haven't talked about how to write a driver for a drawing tablet, so you just have to check the documentation of some drawing tablet and follow it in order to implement a driver. Or, for example, a web browser that's going to need a whole network stack. So you're going to need to implement a server in your operating system that is going to provide some sort of internet service, right? It provides a whole network stack, such as the TCP/IP stack. So it needs to communicate, needs to send Ethernet frames. You have to implement the IP protocol, some transportation layer protocols such as UDP, TCP. So and then obviously app-wise, you know, the application itself is going to communicate through things like HTTP, if it was like it's like a web browser or something. So when there's a program, well, the summary, I mean, this is very simple in theory, and obviously very difficult to actually do, but it can be done with enough research and time. Now, when there's a program and you want to port it, you have to make sure it supports all the system calls, and sometimes to support the system calls, you'll also have to think about services and drivers that you haven't implemented yet. So that's basically the idea. You have to design your operating system in a way so that you can port as many sort of programs as possible. And if that isn't possible, well, you'll have to sort of modify the software and such, such that it can be ported. So, so that's one thing that the user expects, that, you know, he has software that he can actually interact with and use. But he actually wants to interact with it in real time. So what I've sort of implicitly have also been making is an RTOS, or real-time operating system, which, I mean, as I said, I haven't fully highlighted it, but that's what most modern operating systems are, or at least the most popular ones, because I don't know if you actually took a look at the numbers, I don't know, but I think RTOSs are a huge part of operating systems. And RTOSs, vaguely, are operating systems where for any sort of action that has to be executed, you expect some sort of deadline, right? So you want every action within the operating system to be done before a certain deadline. And you split it into sort of two categories. So you could have a hard RTOS, or you could have a soft RTOS. So the thing about a hard real-time operating system is that it has to very rigorously follow the sort of deadline. So it can't miss the deadline. It is absolutely forbidden, and it has to use techniques such as resource reservation. And the idea of resource reservation is that if the RTOS is not 100% certain that it can execute the process before the deadline, it just doesn't do it. Because it absolutely has to do this before the deadline. So an example would be medical systems, right? If you have some sort of RTOS used in some sort of operation room, and it has to do something, well, then obviously it has to follow very rigorous instructions, and you can't introduce standard operating system mechanisms such as preemption, right? Nothing can preempt a process. Any process that is in a hard RTOS always has the highest possible priority and has to be executed before this deadline. If it's not possible, the RTOS doesn't even take on the process if it's not possible to do it without a guarantee of completing it in a sufficient time. So obviously, as one might guess, that's not the sort of operating system that we're making, because we're introducing things like preemption and lowering priorities and queues and like MLFQ and things like that. So obviously it's not going to be a hard RTOS. We're making something called a soft real-time operating system, which a user sort of expects, because a user doesn't want the process to take, you know, forever, or, well, they don't want, for example, the launching of a process or whatever to take forever. They don't want for their operating system to be sort of unpredictable timelines. They still expect some sort of deadline, and the deadline is supposed to be quick. Soft RTOSs, they still have this notion of a deadline, but they don't actually care that much about following it so rigorously. They try to do everything possible so that the user gets a real-time experience. But if something goes wrong, it doesn't care that much. And most operating systems used nowadays on personal computers are soft real-time operating systems, right? So in soft real-time operating systems, you still sort of care about this real-time thing. So there are a couple of mechanisms that you could introduce in order to ensure that this operating system is real-time, such as prioritizing real-time processes. So if you have some processes that have to, are very interactive, and the user sort of constantly, provides input and something happens, and it has to truly give this idea that he's interacting with the process in real time, then it has to be given a higher priority than processes that are just executing in the background or not doing anything important, and the user doesn't have a constant interaction with them. So this is one thing that could be done, and another thing, which is a bit difficult, but you sort of have to think about it, is to minimize the expedition time. So I sort of talked about context switching, and I talked about how we try to give the user an illusion that they are able to multitask and they're able to interact in real time with multiple processes. Now, in order to truly make an RTOS, because you'll see that just standard context switching has a lot of problems. For example, if there's a syscall occurring or an I/O operation, and you sort of have to care about those special cases. And you have to do everything that you can in order to minimize the expedition time. And the expedition time is the time that it takes when you let a process know, hey, this other real-time process, it currently needs to be executed, and you're supposed to be preemptive. And this is difficult, as I said, for example, if a syscall is happening, because syscalls, that you can't just exit the syscall at any moment. Or, well, if you design your operating system that way, you can, but that's the thing. So there are like two main solutions to minimizing the expedition time. One is to introduce breakpoints in your system call. So like, not at every point are you going to be able to exit the system call, but there are some points where you could consider, okay, actually nothing's going to happen if we switch to a different process at this point of the syscall's execution. So you introduce those breakpoints at which you can switch to another process, and this is going to minimize the expedition time. It's better than finishing the syscall up to the end. And then the other thing is you could theoretically make a preemptive kernel. So not only can you perform preemption processes and say, hey, I'm going to take your CPU time, I'm going to give it to another process, but you can also make a preemptive kernel, so the kernel can stop giving itself CPU time and give it to a process. And this is very difficult because it requires for you to design your system calls in such a way that they can be sort of saved at any moment, they can be executed from that point, and nothing is going to occur. That is very difficult. So the breakpoint solution usually works a bit better. It's definitely better than having to wait until the end of the system call so that control is given back from the kernel to the process, then the process can be preempted. It's still a solution that minimizes expedition time, and making a preemptive kernel can be very difficult. And yeah, generally, like minimizing all the sort of things that usually you measure scheduling with sort of all those different properties. For example, average waiting time, right? So the waiting time is the time that the processes in the system, but its code is not being executed, right? Or for example, response time. Response time is the time it takes from a process to enter an operating system and the time that it is actually started to be executed at. So intuitively, it's often presented as, you click an icon, what time does it take for the window to actually appear? Which is not 100% accurate, because, well, the window creation might, for example, occur at a later moment of the process and such, but it's this sort of intuition. So things like average waiting time and everything, you want to minimize it as much as possible, so you give that a sort of feeling of it being a real-time operating system, a soft real-time operating system. And going back a bit into the sort of priorities, you have to make sure, absolutely, that those real-time processes, I mean any process, but especially real-time processes, for the priority not to be moved down to such a level that you're not being given any resources anymore, especially not like CPU time and such. So this is called process starvation, right? Processes starve when there's so many more like processes that have a higher priority, such that the one that is being started is never executed, or it's never given some sort of resources that it needs because it's given to other processes. So you have to especially avoid that. If it comes to real-time processes, you never want to start processes that are real-time, because, well, that entirely removes the real-time part of a process, right? So you have to make sure, if you want this to be, sort of a modern personal computer operating system, that would have to be a soft real-time operating system. Yeah, so that's basically what the user expects. They expect software that they can operate on, so obviously you have to port that, you have to make your operating system support ABIs and such. And there needs to be, you need to implement some sort of mechanisms for this to be a soft real-time operating system, so the user feels like we're interacting with all the different processes in real time. So that's pretty much everything that I wanted to talk about if it comes to, well, just the actual part of the lecture. But I'm just really glad overall, to summarize pretty much the whole series. I'm really glad that I managed to finish this, but I'm standing here right now. I mean, I was standing where I always was, but I'm standing here and I'm saying this. I'm saying that I finished the series, and I have met all the requirements that I originally wanted to meet. Everything that I originally had in mind for this series worked out. So, I mean, we have achieved a lot, because sometimes superficially and sometimes more in depth, but I covered pretty much all the most important things related to starting developing your own operating system. Because I've talked about how a bootloader works. Even if you don't make your own, it's good to know how it works from a theoretical perspective. But obviously it's perfectly fine, and I'll even recommend it if you just use some different bootloader. Well, I've talked about handling interrupts, and because of that, I/O devices, and then managing memory, managing a file system, and then scheduling processes, giving them the right CPU time, and managing the resources, of the processes. So, how you can actually run processes, and how we're given all the different resources, and then, I talked about the fact that now you just have to port software, and is going to use all of that, and we have this foundation of an operating system that can actually run things and give this perception in being real time. So it's a relatively good start. Definitely I hope that I was able to be some sort of additional resource that was able to clear some things up. And I hope that I've helped someone through a journey of sort of making their own operating system. And well, if you've sort of done at least a bit of everything that I've covered, I mean, be proud of yourself. You've just made an operating system. What you've created is an operating system. The user runs different programs and doesn't care about what's going underneath them and just enjoys the process of interacting with them, and all of that works on, just pure hardware. And I think that's something to be proud of. If you've accomplished that. So I'm really happy that this worked out. This probably will not be obviously my last video on YouTube. It's not like that. I will probably still upload some videos related to computer science, probably more related to mathematics. And I hope that we'll see each other in some video in the future. I'd like to thank everyone again for the really immense support that I've received for recording the series. If you have any thoughts to share, any sort of comments, I would be really glad to hear them, whether on YouTube or whether you contact me privately. I'm always very happy to hear things. If you have any questions about the series, any questions about the operating system development in general, I'll try my best to answer them. I'm happy that, despite having relatively little time throughout the previous year, I managed to do the research, record the videos, hear some of the feedback, and keep on going and make this sort of relatively complete operating system development series that I've always dreamt of doing for years on end, really. It's been a very long time since the sort of thought, popped up in my head. As early as I think 2021, I started recording some videos that are currently either private or unlisted. And there I was already talking about sort of operating system development. I've always dreamt of doing this sort of series where I can talk about, all the foundations that are required to make a basic functioning operating system. So this is a pretty important moment for me, and I hope that maybe it's also an important moment for some other people, or at least one person who has maybe followed this series, and I hope that I've taught someone something. Thank you, everyone. And maybe not in the operating system development series, but I hope we'll see each other somewhere in the future.